Hello and welcome everyone. In this video, we will start learning about the simplex method, which is a key algorithm in linear programming. It can efficiently navigate through the feasible region to reach the optimal point, thus maximizing or minimizing the objective function. The simplex method moves from one extreme point to another adjacent extreme point and ultimately reaches the optimal extreme point in a finite number of steps. Here, we will review the algebraic simplex method, which uses some algebraic calculations with equations. The next video will be on the simplex method in tabular form, where we will see how to use a table to organize these calculations. Okay, to understand how algebraic method works, we will solve this example in a step-by-step way. So let's get started. We can see this problem is in its standard form, that is, it satisfies these four requirements. The simplex calculation will be started with the canonical form of the problem. So we will need to write the problem in its canonical form. If you haven't seen the video on canonical form, it's the previous video in this series. I will also post the link in the description. In the previous video, we saw that in canonical form, we use basic and non-basic variables, and the total number of basic variables should be equal to the number of constraints. Here, we arbitrarily choose x1 and x2 as basic variables and x3 and x4 as non-basic variables. After some manipulation, we can write the canonical form, and we can see that in this form the objective function is written purely in terms of non-basic variables, and each constraint has exactly one basic variable with coefficient 1. To get the basic feasible solution, we can set x3 and x4 to 0, and then from the constraints we can get x1 is equal to 34 and x2 is equal to 26. Now, after plugging these values into the objective function, we get z is equal to 141. Now, we got one basic feasible solution, but the key behind the simplex method is to move from one basic feasible solution to another that gives a better value of the objective function. And how do we do that? Previously, we arbitrarily selected x1 and x2 as basic variables and x3 and x4 as non-basic variables. Now we want to replace one variable in the basis with one non-basic variable. The optimality condition states that the value of z can be improved if at least one of the coefficients of the non-basic variable is negative. And here we can see both non-basic variables have negative coefficients. In this case, we will pick the non-basic variable with most negative coefficients and replace with the one in the basis. Based on the criteria, we picked x3. The next question is which basic variable x3 will replace. For that, we review the constraint equations, setting x4 equals to 0 and solving for x1 and x2 gives these equations. Since x1 and x2 are both non-negative, we can see that first equation yields an inequality where x3 is greater than minus 17, whereas the second equation yields an inequality where x3 is smaller than or equal to 26 by 3. Since the first inequality does not have an upper bound on x3, the upper limit is entirely determined by the second equality and x3 equals 26 by 3. Therefore, in this case, x3 will replace x2 for the next basic feasible solution. Now, the basic variables are x1 and x3, and non-basic variables are x2 and x4. We will update the canonical form of the problem for these basic and non-basic variables. Then setting x3 is equal to 26 by 3 yields this basic feasible solution. And this solution, when placed in the objective function, yields a value of 514 divided by 3, which is greater than the solution from the previous feasible solution. Now, since the coefficients of all non-basic variables in the z equation are all positive, this shows we cannot further improve the objective function as per the optimality condition. Therefore, the optimal solution in this case is x is equal to 154 divided by 3, x2 is equal to 0, x3 is equal to 26 divided by 3, and x4 is equal to 0. This concludes our video on algebraic simplex method. I hope you liked this video. Thanks for watching and see you in the next video in which we will review simplex method in tabular form.